Okay, guys, I'm just going to do a quick lecture on the lymphatic system and immunities. I have in here a couple of videos since you're going to miss out on my very exciting stick figure drawings on the board for these. You'll just have to watch the videos and watch somebody else's very exciting stick figure drawings. Okay, so the lecture itself, or the PowerPoint itself, is pretty short, but we'll get through it, and hopefully these two videos will help explain anything that is maybe not super clear. I am here during the week that you guys are gone, so I'll be here the 18th, 19th, 20th, and 21st. So if you have questions, you need to get a hold of me, email me through my College America account, because I will likely not be on Canvas. So if you send me an email through Canvas, I may not see it, except for when I open it up to put grades in. So if you have questions or you need to get a hold of me, email me through my College America account. Okay, let's get started here. So the lymphatic system plays a big role in our immune system. And oftentimes when we get sick, you probably remember this when you were a kid, but when we get sick, our parents would feel underneath our jaw, along our throat, and feel for swollen nodes. Now, those swollen nodes are literally swollen lymph nodes, and lymph nodes are, excuse me, are biological filters that trap, trap pathogens. I was eating some popcorn and now it's going to kill me. Sorry about that. Okay, so interstitial fluid is the fluid that is the tissues and that is in between the tissues. I think when we think of fluid, we usually think of blood or urine, but we have lots of fluid in our tissues, and that's called the interstitial fluid. Okay, and then lymph nodes, or lymph, is what circulates throughout our body, and the lymph fluid joins into our lymphatic system, and we have a whole set of lymphatic vessels that are similar to blood vessels, and in fact they work side by side with our blood vessels. So if we go back over here to the cardio-lymph interrelationship, you see how similar they are. I know I've mentioned throughout this class that all pieces of our body work together and we have backup systems. So our circulatory system moves blood, but it also works right alongside our lymphatic system. So this is all interstitial and lymph fluid, which is a huge part of our immune system. So you'll see how closely it matches the circulatory system. So what happens is the heart pumps down here, so the blood leaves through the artery, and then arterioles, and then capillaries, and the lymph actually meets up with our capillaries, and that's where it dumps the interstitial fluid. Then through skeletal movement, the lymph and the blood are moved back up towards the heart. And then these are the nodes, which I said are biological filters. It's like a coffee filter for your immune system. So as the fluid comes in, when it hits a node, the node, if there are any pathogens or white blood cells or inflammation in here, it's going to get trapped by this filter and then move on, so that by the time it gets to the capillaries, it should be pretty well clean. It should be. The problem is that if somebody has, say, a lymphectomy because they've had a mastectomy, they had breast cancer, they had their breast removed, cancer, the lymph nodes often are inflamed because they're trapping as much of the cancer as they can, so they remove these. And so when we get into phlebotomy class, we'll talk about drawing blood on people who have had mastectomies, and the general rule of thumb is we don't do it on the side of a lymphectomy because this filter, we've physically removed this filter. So any pathogens that we inadvertently introduce during the blood draw procedure can go straight into their bloodstream, and that's a big problem. So you can see how how closely related these two systems are. Let's see, I've talked about lymph nodes. Lymph nodules are just slightly different than a lymph node. Excuse me. And I did not mention that lymph moves only in one direction, which is towards the heart. I did mention that it's through skeletal muscle contraction that moves it. We have macrophages, which means big eaters. Phage means to eat. Macro means big. So these are big eaters. We also have lymphocytes, which means lymph cells. Okay. And the macrophages are part of our non-specific immune response, which you guys will watch a video on. But it's just any foreign invader gets attacked. We have different types of non-specific immune responses. We've got the barriers, the physical barriers like our skin and our mucus and our stomach acid. And then we've got things in our blood like macrophages, which they don't care what specific type of pathogen it is. If it's not self, they kill it. Okay. And then lymphocytes are also lumped in with white blood cells, and they're part of our immune system. Okay. Our tonsils are masses of lymphatic tissue on each side of our pharynx, okay, on each side of our oropharynx. And we all know somebody who's had them removed. Maybe you had them removed yourself. If they get too inflamed, then we just take them out. Our thymus and our spleen are super important to the lymphatic system. Our thymus is where our T cells mature, and our spleen, in the cardiovascular system, our spleen is the red blood cell graveyard. But, excuse me, in our lymphatic system, it helps by removing those red blood cells, but it also filters the lymph fluid as it comes through. We can live without a spleen. Our liver takes over the functions of the spleen. So if somebody is in a car accident or something and damages their spleen, they'll do a splenectomy, remove the spleen. The liver takes over the job of filtering the lymph and also of breaking down the red blood cells and reassembling them. Okay. We have our non-specific immunity, which I mentioned just a second ago. It's also called innate immunity. They're just species resistance. Just means that there are diseases we can't get because we're the wrong species. So there are diseases that can wipe out whole acres of crops, but we're not going to get sick because we're not plants. So that's species resistance. We get the common cold, but our house plant doesn't. It's because the plant is the wrong species. So that's a non-specific defense. We have mechanical barriers. Our skin, our mucous membranes, those are all physical mechanical barriers that that do not allow pathogens, or I don't think I've just defined what a pathogen is. A pathogen is anything that can cause disease. So it can be a parasite, a virus, a bacterium. Those are usually the big three. There's also prions, but I don't know that our mechanical barriers work great against some of those itty bitty tiny things. So skin and mucous membranes, those are our mechanical barriers. Our chemical barriers are things like our saliva and our mucus itself. Our stomach acid, those make the environment for the pathogen not super welcoming. So then the pathogen either dies or doesn't hang around. Phagocytosis is super cool. It just means eating cells. Remember I said macrophages are big eaters. Macrophages eat by engulfing the pathogen, and that is called phagocytosis. Fever is also a non-specific defense. So bacteria especially live in a very specific temperature range. And if it gets too hot, they die. Or if they get too cold, Sometimes they can form spores and hang out till conditions are right, but typically they die with heat. So our body, when we start to get sick, cranks up the temperature, cranks up the thermostat to kill whatever it is that we've been infected with. Low-grade fevers are typically not a problem. We really start worrying about 102, 103. But if you have a low-grade fever and you're feeling okay other than just tired, then you may decide to just let the fever run. But once it starts getting high, you start getting the fever chills and the hallucinations and the bad things, then we might think about taking some Tylenol or Advil or both of them to bring them down. Inflammation is also a non-specific defense, and the four parts of inflammation are pretty standard. It is pain, redness, swelling, and heat. And this is in response to injury or illness. So if you sprain your ankle stepping off a curb, your ankle is going to have pain, redness, swelling, and heat. If you cut yourself during Christmas baking, you're going to have pain, redness, swelling, and heat. That is just what happens when we have inflammation in our body. And the reason that we have the pain, redness, swelling, and heat is because the blood vessels dilate to bring more blood to the area. Blood is red, so that causes the redness. The swelling is because of the increased blood flow to that area. Pain, swelling, redness, pain could be, number one, the pain from the injury, but also we tend to get a throbbing pain with this, and that's because of the increased pressure in that area. And then heat can be because of with an initial injury, you're going to have heat because of the increased blood flow, which makes it a little bit warmer. But if it's an infection, if it's been a couple of days, then the heat could be a localized infection, and now you're going to have a bunch of pus and nastiness coming out. NK cells are natural killer cells. They have the coolest name ever, I think. Their primary job is to target cancer, but they can kill any pathogen. And it's just the coolest name ever, isn't it? Okay. Specific defense is when we have a specific pathogen, like the influenza A virus is a specific pathogen. So our body sees it, knows that it doesn't belong. Remember, I said our immune system's job is very easy. It's self or not self. So when it sees inflammation, or when it sees influenza A, it says, hey, this is not self, and it attacks it. Well, by the time it's killed the influenza A, it has also cataloged what it looks like to the body. So the next time we see that exact strain of influenza A, our body immediately makes the antibodies and attacks it, and we don't get sick. So that's how our immunities work. Okay. Peptins are just really small pathogens that are really too small to be a problem, so our immune system kind of ignores them. The complement system is a cascade, and you'll talk about cascades in LBT 205, which is hematology class. We talk about the coagulation cascade. The thing with cascades is that they're like a domino effect. So once it gets started, it does not end until it gets to the end. So once the complement system is activated, it's like dominoes falling. It just calls for help from all of the other complements, and you get an overwhelming response of your immune system, which is a good thing most of the time. It would maybe not be a good thing if it was an autoimmune thing where your body's attacking itself and triggers the complement cascade. You can't stop it, because once it's like trying to stop a domino as it's falling. It's, can't do it. Cytokines and monokines are the messengers of the immune system. So they're the ones that can call for help. They can say, hey, come here. They also can bring in it's still part of calling for help. They bring in other cells to help fight the infection. So within our specific defense, our immune system, we've got B cells and T cells. B cells mature in the bone marrow, so that's how you remember it, B and bone marrow. and T cells mature in the thymus. Okay. In children, babies to about age 5, the thymus is huge. It does not grow as the babies grow. We tend to outgrow our thymus. But the reason that the thymus is so huge is that it's so busy building antibodies. It's really important to, number one, get your vaccines for your kids, and number two, let them be exposed to things, because that is the thymus's prime time of its life, is from birth to 5. It is cranking out antibodies. And what we found is that children who are not exposed to things, not allowed to go outside and play, not allowed to get sick, those children, when they get to preschool, excuse me, when they get to kindergarten, have far more sick days than the kids who were allowed to get sick and play in the dirt. Because the kids who, or go to get daycare, if kids start in daycare, they're sick all the time when they start in daycare, right? If you guys ever have kids that have gone, they're sick the first 6 months of daycare, but then their immune system is bulletproof. They never miss a day of kindergarten. Yet the kids who were never allowed to be sick or be around sick people, their immune systems are underdeveloped, so that when they get to kindergarten, they are so sick the whole time. So our thymus is super important, and it's important to let our kids play in the dirt and get dirty and be sick, because it really does help their immune system. Okay, so I kind of got off on a tangent there. So B cells and T cells. Okay, so a cell-mediated response that is up here is initiated by the T cells. Okay, so the T cells see the antigens. They say, oh, wait a minute, you're not supposed to be here, and call in lymphokines and macrophages, and they call in the help. The T cells will see it and go, you're not our kind, you've got to leave, and attack them. Okay. This is supposed to be lymphokines, not lymphokines. There we go. So it's supposed to be lymphokines. So T cells activate the cell-mediated response, which activates the lymphokines that activate the macrophages, that then starts killing the pathogens. An antibody-mediated response happens outside of the cells. It happens in the fluids. And the way that works is, remember I talked about the interstitial fluid? So that is where this antibody-mediated response occurs, is in the interstitial fluid. And I mentioned that our immune system has one job, and that is to differentiate self from non-self. So if it decides that something is non-self, it attacks it. And the way it can tell whether it's self or non-self is through the MHC, the major histocompatibility complex. If you're self, it recognizes your MHC. If you're not self, it doesn't recognize it, and it attacks it. This becomes a problem with organ transplants. So one of the things that they test for before they do organ donation is the MHC, to see if it's close enough that they could hide it from the recipient's body, so that the recipient's immune system doesn't freak out and kill what was just transplanted. The immunoglobulins, these are just immune proteins, and each one has a specific function. I'm terrible at remembering these. What is important for us is that when we are looking to see if somebody is immune to something, we will draw a titer, and the titer will tell us if they're immune, and they look for specific things. The hematologists and immunologists who work with this have this down pat. I am terrible at remembering it. Although as an MA, I'm not required to. I just need to know that the immune proteins will help us know whether or not somebody is immune to something. Now, this is important to us, the different types of acquired immunity, and this will be one of our interactive notebooks for the week. So we can acquire things two ways. We can acquire it either naturally or artificially. Okay. Naturally means, hey, we got sick, we got the antibodies, yay. Okay. Artificially means that it was made in a lab and we somehow acquired it. Okay. We somehow got it, but it did not naturally occur in our body. It was made elsewhere and then we got it. Okay. So a lot of people get stressed out by this, and there's so many words, and they freak out a little bit. Acquired just means that we got, somehow we got it. Natural means we got it naturally. Our own body had this. Artificially means it was made probably in a lab, just like natural sugar and artificial sugar. One comes from the environment, one comes from the lab. Active means that our body had to do the work to make the antibodies, whereas passive means our body was given it to us. Or given, that didn't sound right. Our body was given the antibodies. We didn't have to make it. Our body, our immune system sat on the couch, ate chips, drank beer, while somebody else's immune system did the work, and we are benefiting that. So do not freak out when you see all these naturally acquired active, artificially acquired active. You know what each word means. You just have to put it together. So naturally acquired passive. This means it was not made in a lab, right? Because it's natural. Acquired just means we got it. And passive means that our body's immune system just sat on the couch, ate chips, drank beer, while somebody else was giving us antibodies. The only naturally acquired passive immunity that we have is from breast milk to baby. Okay, that's the only passive immunity that is natural. Okay, we have an artificially acquired active immunity would be something like a vaccine, because the vaccines are made in the lab. But the way vaccines work is that we introduce killed pieces of the pathogen to our body. Our body says, oh my God, you don't belong here, mounts a response to it, builds its army, and the army is antibodies. So our body is actively fighting what it thinks is an infection, and it's not. Artificially acquired active immunity is what happens with vaccines. We trick the body into thinking it's going to get sick, and then it makes the antibodies. So when it sees that disease again, it just immediately kills it. Naturally acquired is when we get sick, and then we are immune. So people of my generation had chickenpox parties. We all got together, we all had chickenpox, now we're immune to it. Okay, so it was naturally acquired, it was not made in a lab, and our bodies actively made the antibodies. Okay, so hopefully this makes sense to you. Some of the common diseases, autoimmune diseases are, I feel like they're on the rise, but I don't know if that's actually true or if we're just more cognizant of them and we recognize them more. 20 years ago, we had no idea what an autoimmune disease was, but now we have so many of them. So like I said, I don't know if it's on the rise or if we finally know what they are and we are able to diagnose them, whereas we couldn't in the past. Cancer is an overgrowth of tissues. Our cells just go crazy and keep growing, and they're not supposed to. Allergies are a sensitivity to something. They're not supposed to be, our body is not supposed to overreact, but something, usually called an allergen, if it causes allergies, it's an allergen, just like a pathogen causes disease. So some allergens cause our immune system to act up. And most of the time when our immune system acts up, um, it's simply the runny nose, stuffy nose, runny eyes. If you've ever had spring fever, you know, the allergic rhinitis that goes with it, that's a usual reaction to allergies. However, anaphylaxis is life-threatening. That's when we get exposed to an allergen that our body completely becomes a drama queen and freaks out about, okay? It dumps so much, the immune system gets so active and it dumps so much histamine, lymphokines, and all of it takes everything for this one little allergen, freaks out. The problem is that when you look at the four classic signs and symptoms of inflammation, redness, pain, swelling, and heat, when an anaphylactic reaction happens, all of those happen, but they happen on a much grander scale, which means that throats can swell shut, people get bright red and flushed, and if their tongue swells, their throat swells, they can't breathe. Anaphylaxis is a big, big deal and a life-threatening emergency. So people who have allergic reactions or who may have allergic reactions often carry an EpiPen just in case of an anaphylactic reaction. Okay. AIDS is caused by a virus that wipes out our immune system. Chronic fatigue syndrome is, nobody really knows what chronic fatigue syndrome is. They think it is now an autoimmune disorder that just causes unbelievable fatigue. Like, you can't get up, you're just exhausted all the time, and not normal parent exhausted, but like breathing is too much effort kind of exhausted. Okay. Lymphedema, if you break that word down, you could probably figure it out, okay? It is swelling in the lymphatic vessels. So if we have swelling in the lymphatic vessels, then fluid can't get through and it starts to back up and we start getting swelling distal to that point. So this is not very good for our immune system. It's also not very good for our circulatory system. Mononucleosis is typically caused by the Epstein-Barr virus. This causes hepatomegaly, which is enlargement of the liver. And so a lot of kids end up with this in junior high, high school. They called it the kissing disease when I was in junior high. And this completely sidelines kids because of the hepatomegaly. It sidelines them for 6 weeks or so. So they're tired all the time. They may be jaundiced a little bit, but really it's no contact sports, no anything until it runs its course. Okay. Lupus is another autoimmune disease that we don't know a ton about. They're doing a lot of research on lupus, but there's really, they believe it to be an autoimmune disorder, but it presents in different people in different ways. There's some common things, the fatigue, the lowered immune system. There's some commonalities for lupus, but no two people with lupus present exactly the same, which makes it difficult to treat. And then celiac disease is an immune reaction to eating gluten. And I know there are a lot of people out there who are gluten-free. The number of people with celiac where gluten will truly kill them is so small, so small, like 2%, 2 to 3%. It's very small. A lot of people have jumped on the gluten-free bandwagon, but people who truly have celiac cannot have any gluten. And gluten is a binder. It's a glue that holds foods together. And we find it in wheat, barley, and rye. I suppose the good thing about people jumping on the gluten-free bandwagon is now we have more options for people who have celiac disease. But as a general rule, very few people in reality have celiac disease. And those people who do have celiac disease are militant about checking things. People who are gluten-free as a dietary choice will not be as careful. they'll still tend to go out to eat and stuff, whereas people with celiac prepare their food at home for the most part, just because they don't want the allergic reaction that occurs when they eat gluten. Okay, so that pretty much is the PowerPoint lecture. What I don't want to save this, don't save. What I want you guys to do is make sure that you also watch, as soon as my computer catches up to me, I want to make sure that you are also watching the phagocytes in immunity video, so you can get your stick figure drawing, and your types of immune response video. These are both TED Talks, so they're pretty well vetted. Your interactive notebook for types of immunity, this is optional, okay? It is optional. Should you choose to do it, you will just submit pictures of your completed pages. So with this, you will, let's see if I can get it to open here. So with this one, you will fill in the definition for passive, for active. You're going to color code these. I don't care how you color code them, if you color code artificial and natural versus passive and active, but color code them so that it makes sense to you. These are your lines to cut. Okay, so I would glue on this side, cut here, and then underneath, define what each one is. So acquired, passive, artificial immunity, what is that? And then give an example of that. Okay, so that's the interactive notebook for your immunity. For the urinary system, which I'll do a whole separate lecture on the urinary system here in a minute. For the urinary system, you will, again, print the diagram. It is also optional. So you'll color and label the top page. Once you've got it mounted under the left-hand flap, list the structure and function. Under the right hand, the urine flow through the system. Okay. And then just to get credit for it, I want to see pictures. So submit pictures of your completed pages. So label here, label all of your structures. Cut up through here. Left-hand side will be structures and functions. Right-hand side will be urine flow through, starting here with the renal artery and renal vein until it exits the body. Okay, so I'm going to call it a day on this lecture. I'll get this one uploaded, and then I will start in on the urine lecture, which may not actually be up until, what is today? Today's the 13th. So urinary lecture may not actually be up until sometime tomorrow, the 14th, but I will definitely have it up before you guys leave for break. All right, if you have any questions, let me know. Thanks.